Hi, so for the first part of chapter 10, we're going to be covering from the very beginning on page 270 until page 280, all the way up until physical characteristics of lipids. As usual, this first part is going to be the more food chemistry heavy part, and then the second part will be more about functionality and nutrition. So diving in here. So lipids define their category of organic compounds. So organic means that it's carbon-containing compounds that are insoluble in water. Um, so they do not mix in water. Um, the book says that they have a greasy feel. I am crossing that out because not all lipids have a greasy feel. Only some of the lipids do. Um, for example, the steroids, cholesterol, those would not have a greasy feel if you were to hold those in your hand. Many of the lipids do, but not all of them. So I crossed that out because that's not really part of the definition of lipids as a whole. But they are soluble in organic solvents, um, and they include fatty acids or their derivatives. Finally, like carbohydrates, they contain carbon, hydrogen, and oxygen, but they're not contained in the same ratios as carbohydrates. So it's not carbon plus H2O. Um, it's a different ratio. Um, and they do not, as part of their definition, they do not provide structure to food products. Nothing about them is required for structure of what you are making. They do not dissolve in water, which really just goes along with this insoluble in water portion. And they do not have a polymer construction. So what I mean by that is with the carbohydrates, for example, we would have a glucose molecule and many glucose molecules all chained together made a starch molecule. Well, lipids aren't like that. They have a very defined structure, and it's not a polymer, which a polymer is a group of molecules that are joined together. Um, so yeah, so they're not built like starch, for example, where you just add on more glucose and it's still starch. So the first category of well, actually, hold on. Yeah, the first category of lipids that we'll talk about are triglycerides, and these comprise the majority of lipids that we consume, that we use as ingredients, etc. Okay, and the glycerides have a base of this molecule here called a glycerol molecule. And so you notice that it has 3 carbons and our old friends here, the hydroxyl groups. We have 3 hydroxyl groups that are part of glycerol. The all ending of the name glycerol indicates those hydroxyl groups. Glycerol is an alcohol, and it is an alcohol unlike carbohydrates because it only has these hydroxyl group as functional groups. CH2 carbon is not a functional group. Okay, so we noticed that here. And attached to the glycerol molecule are 1 or more fatty acids to make it a glyceride. Okay, fatty acids are defined as organic molecules that have a carbon chain. So you see carbon, 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 and the only thing that is bound to the carbons is hydrogen, all the way up until the end where we have a carboxyl group. And our carboxyl group is where we have the carbon with 2 oxygens and one of which is with a double bond, and the other one is a hydroxyl group. Okay, and so these will be attached to the triglyceride. Here are two examples of fatty acids: stearic acid, which has 18 carbons here, and oleic acid, which also has 18 carbons, but it also has a double bond here in the middle. And we'll talk more about that. Okay, so here's just a list of the fatty acids, and they are classified by the number of carbons that are part of the fatty acid. So just how big this chain is, however big it is, there's always the carboxyl group at the end, and it's just hydrogens and more or less depending on whether there are double bonds. So they're classified by the number of carbons that are in the fatty acid and the number of double bonds. Okay, so for example, formic acid, which is the acid that's found in like fire ant stings, is only one carbon, has no double bonds. So that like fire ant stings are fatty acid that's being injected into your skin. Now, more commonly, most of the fatty acids that we eat, most of them are 16 carbons or more. We do eat some that are in the 8 to 14 range also. And well, even these lower ones too, in some amounts. So like butyric is in butterfat, for example. Acetic acid is fatty acid, and that is vinegar. But so we have like 16 carbons, and then if it has, for example, 0 double bonds, it's called palmitic acid, and there are scientific names that go with them too. Whereas 16 carbons and 1 double bond is palmitoleic, or 18 carbons is stearic, 18 carbons with 1 double bond is oleic, 18 with these are 1 double bond, but just in different places. Another 18 carbon with 2 double bonds is linoleic. 18 with 3 double bonds is linolenic, and etc. Okay, you're not going to have to know all of these common names by any means, but you should start to recognize some of the more common ones. Okay, so a key thing here is that glycerol is polar, right? It has hydroxyl groups. We've already identified hydroxyl groups as polar. Fatty acids are polar overall, but really only the end where this carboxyl group is the polar part. The rest of this chain is nonpolar. There's no charge associated with this. Okay, so the overall charge of a carboxyl group, hydroxyl group I meant, is slightly negative. The overall charge on a carboxyl group is slightly positive. And so what happens is that this carboxyl group and the hydroxyl group are attracted to each other, and they bond and release water when they do so to form the glyceride. And so here's what that glyceride kind of looks like. When I have the R1 here, that is just the rest of the chain of the fatty acid. It could be however long that fatty acid is. Any fatty acid could go there. And so if you look back at the previous slide, we had 1, 2, 3 oxygens and 1, 2 hydrogens between a carboxyl group and a hydroxyl group. And when they bond, we lose one of the oxygens. We now only have 2 oxygens, and we've lost both the hydrogens. And so when that bond is formed, water is released. So 2 hydrogens and an oxygen. So how we term the glycerides, if it can have 1, 2, or 3 fatty acids bonded to a glyceride. Most commonly we see 3, but we can see 1 or 2. And when there's only 1, it's called a monoglyceride. When there's 2, it's called a diglyceride, and 3 is the triglyceride. The triglycerides are what the majority of fat found in the body or in our foods is. Triglycerides can have 3 of the same type of fatty acids, so it could have oleic, 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 or it could have 3 totally different fatty acids that are attached to the glycerol. It could be stearic, oleic, and palmitic, which again, you don't need to know what those are, but they could have 3 totally different fatty acids that are attached to the glycerol. It doesn't have to all be the same. Changing which fatty acids the glyceride is composed of will change the properties, which is really important to know for cooking, for shelf life, and for nutrition, which we'll kind of all cover throughout this chapter. So let's talk about the polarity then of the glycerides. When the bond between the glycerol and the fatty acid forms, you've now neutralized those charges. There was a negative charge here, there was a positive charge here, but they have now combined and canceled out and been neutralized. So that carbon chain had no charge to it. The rest, this here is the same thing. It's just carbons and hydrogens, has no charge to it. Let's look more like at the triglycerides. And so if you have a full triglyceride, then you now have no charge associated with any part of the molecule. There's no charge here on the glyceride end with just the carbons. There's no charge here that previously had a charge because those have canceled out when they bonded together, and there's no charge on any of the carbon chains on the fatty acids. And so now you have a non-polar molecule that has no charge. Now, on the mono and diglycerides, you still have a hydroxyl group that is sitting there waiting. And that hydroxyl group still has that slightly negative charge. So this gives the mono and diglycerides special properties. They actually are somewhat soluble in water. We said lipids are generally not soluble in water, but these actually are somewhat soluble in water because of these hydroxyl groups. They are also soluble in oil because they still have these non-polar parts of them on the fatty acid end, the carbon chains of the fatty acid, as well as on the glycerol. This gives them the special ability, just for the mono and diglycerides, to be used to allow oil and water to mix without separating. So normally oil, water, they'll immediately separate. If you add some mono or diglycerides, you can prevent that to some extent. The oil will be attracted to the fatty acid portion of the mono or diglycerides, and the water will be attracted to the hydroxyl group portion. And so this makes mono and diglycerides good at what is called emulsification. And that is simply being able to allow things that normally don't mix to mix. An example of a food where this would be used is mayonnaise, margarine, nut butters would be examples of that. So the second main category of lipids is phospholipids. And this also kind of breaks the rule about not being soluble in water, because similar to the mono and diglycerides, phospholipids are what we call amphiphilic or amphipathic, which is just a fancy word of saying it's a molecule that's both polar and nonpolar, or in other words, having both a hydrophilic, a water-loving, and hydrophobic, a water-hating part. So hydrophilic is water-loving, hydrophobic is water-hating. Normally, most of our lipids are hydrophobic, they're water-hating. So the phospholipids, they have a glycerol base here. So this is the glycerol that I am kind of circling with my laser pointer here, with 2 fatty acids. So on those 3 carbons of the glycerol, 2 of them have fatty acids, just like a diglyceride. Okay, but the 3rd carbon on the glycerol is bonded to a phosphorus containing acid. Okay, and this phosphorus part, as well as the rest of the glycerol, is, well, really, the phosphorus part is water-loving, it's hydrophilic. The fatty acids, of course, are hydrophobic. They're still nonpolar. This phosphorus part is polar, it is water-loving, and the fatty acid is nonpolar and hydrophobic. Okay. So this part is soluble in water, while this part, the fatty acid part side, is not. So phospholipids can also interact with both fatty substances and water at the same time, making them good emulsifiers. Like the mono and diglycerides, phospholipids can be used to keep foods that have water and oil from separating. They are not really very commonly used in the food science field. They're really more important to know about them from a biological perspective. So phospholipids are part of the lipid bilayer, which you should have learned about in biology, of the cell membrane. Okay, so they are the exterior, they are what the cell membrane is made out of, along with the proteins and things that are part of the cell membrane that allow transport. Okay, so because you have the hydrophilic head, the phosphorus side, and the hydrophobic tails, what happens is the hydrophilic sides are on either side of the cell membrane, facing towards the water part of the interior and exterior of the cell, right? Inside the cell, there is the cytosol, which is composed mainly of water, and outside of the cell, it's also going to be a aqueous environment. Okay, and the hydrophobic parts will face towards each other. Will be attracted toward, or not, will face towards each other. Okay, so there are some substances that can easily pass through this plasma membrane without any help through osmosis. And there are other substances that, in order to get through, they need helpers, so proteins that allow or disallow substances from coming in or outside the cell. Okay, and so that is their main function. They don't have a huge food function. It's more so phospholipids as a biological function. Okay, and the third type of third category of lipid is the sterols. These are derived from lipids. So we said that kind of the lipids were like either, and I should say derived from fatty acids, but either, include or derived from fatty acids. Well, these are derived. So sterols are a steroid with a hydroxyl group, and they too are amphipathic. So like this part of the sterol is polar, but this part is nonpolar. So it has both polar and nonpolar parts. But we don't use the sterols as food additives because they have major functions in the body, and generally not something that you want to use as a food additive. So I'll say we do sometimes supplement with vitamin D, which is a sterol. So cholesterol here is part of every cell in the human body. We absolutely need it to function. We also need it to make testosterone and estrogen, our sex hormones. And so this is the pathway here for how that's done. Cholesterol is turned into progesterone, which is then turned into aldosterone, testosterone, or cortisol, which is a stress hormone or stress steroid, I guess. Stress hormone. And then testosterone can then be converted to estrogen, which another name for estrogen is estradiol. Okay. We also need cholesterol to make vitamin D in our bodies. So you can consume vitamin D, in the form of taking vitamins or milk that has vitamin D added to it. But you can also make it in your body, and to do that, you need cholesterol plus, and this is cholesterol that's been modified a little bit. So you have cholesterol, then it goes to dehydrocholesterol, ultraviolet light, and then your body can go through the process of making vitamin D here. So now we'll go through ways that you can categorize fatty acids. And the first one is based on their molecular structure. So when all of the valence, so let's look at this Lewis structure first here. When all of the valence electrons, so all of that outer ring of electrons of the carbon are bonded with hydrogen. So carbon has 4 valence electrons, the ones that are close, that you see closest, 1, 2, 3, 4. When all of them are bonded with hydrogen or another carbon, then the molecule is said to be called saturated. Okay, so let's say this carbon here, we have the 4. One is with hydrogen, one's with hydrogen, one's with hydrogen, and one is with carbon. This is a saturated molecule. But if there are fewer hydrogen, the carbons can and will form double bonds with each other to fulfill the bonding requirements. So in this case here at the bottom, this carbon on the right, 2 of the valence electrons are bonded with hydrogen, and it would have a third one that needs to be bonded with hydrogen, but there's no hydrogen there. And so instead it's going to form a double bond with the carbon, and both of these do that, and fill up those valence electrons that way. But now this molecule is unsaturated. It is not saturated with hydrogen, unlike this one at the top. Okay, so that is what the saturation, when we're talking about this next part, saturated and unsaturated fatty acids, unsaturated and saturated fatty acids refers to. So now on a bigger fatty acid scale, a saturated fatty acid, that is what this looks like. Okay, so you have this carboxyl group. You kind of just ignore that. Don't look at that. But look at the main carbon chain, just carbon, 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 and all the hydrogens bonded to it. And you see that every carbon has 2 hydrogens bonded to it, except for the ones at the ends, which would have 3 because they don't have another carbon to bond to. Okay, so all 4 of each of these carbons' valence electrons is occupied by either 1 carbon or 1 hydrogen. And there's no pairs of valence electrons that are having to double bond to a carbon. This one here, it's the same fatty acid as far as number of carbons that's in it. Both of these have 18 carbons in the chain, but in the second one, which is oleic acid, these carbons here each now only have one hydrogen that they're bonded to, and they have a double bond to fulfill those valence electron needs for bonding. Okay. Now, what you should notice here is that this stearic acid that was saturated is nice and straight. When we introduce this double bond, it causes a kink in the molecule, and it is no longer straight. It has a bend in it, and that is going to come into major play as we're talking about functionality of these fatty acids. Now we can also have more than one double bond. Any fatty acid that has more than one double bond is called polyunsaturated. Okay, so examples here. So palmitic acid has 16 carbons and it is saturated. These here are just another way to draw what is here. We've talked about this before. We've just taken out the hydrogens and they are assumed. And anytime that we just have these lines at whatever corner there is, it's a carbon. Okay. So starting right here, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and then it actually writes out the last one, 16 carbons on palmitic acid. Okay, so the oleic acid is the same one that I showed on the previous slide with 18 carbons and one double bond. And so this is called a monounsaturated fatty acid when there's only the one double bond. Okay, the rest of these are polyunsaturated fatty acids, and we won't get into the difference between omega-6 and omega-3 right now. But the point being that they have 2 or more double bonds. So the double bond in these figures is represented by that little extra line that you see right here, here, here. So this one has 2 double bonds. Linoleic acid, arachidonic acid has 4 double bonds. Alpha linolenic has 3. Icosapentaenoic has 1, 2, 3, 4, 5. And docosahexaenoic has 6. So all of these would be polyunsaturated fatty acids here. Now, what really notice here, how these shapes are affected by the double bond. Every time you have that double bond, there's another kink. And these shapes are really going to affect the physical properties of these fats. So lipids that have more double bonds have a shape that does not lend itself well to stacking in a nice, neat structure. I mean, we've talked about this with the carbohydrates, right? And so therefore, the ones that really just cannot stack like this are going to tend to be more liquid at room temperature. They tumble over each other, okay? Whereas the saturated fats that are nice lines can stack well and be more organized and tend to be more solid at room temperature. There's a little bit of an exception based on how long the saturated fatty acids are, which we'll get to later in this slide set. Oops. Okay. So saturated fats, where we get them. Animal fats are the biggest source of saturated fats, but we also get them in from some plant sources such as coconut oil and palm oil. Monounsaturated fats, sources for those include olive oil, avocado oil, canola oil, sunflower, safflower, peanut, lots of different plant sources. Also nuts. Some polyunsaturated fats sources include corn oil, cottonseed oil, peanut oil, soybean oil, sunflower, canola, flaxseed. Now notice, oh wait, one more, fish. Oh, one more. soybeans, chia seeds, and walnuts. Now notice how some of these have multiple sources. And you can even find monounsaturated and polyunsaturated fats in animal products. So, these lists here are like the main sources for these, but we will find both mono and polyunsaturated fats in animal products, in coconut oil, in palm oil. Um, um, and especially in if you have, for example, if you have animals that have consumed more polyunsaturated fats as part of their diet, you'll actually usually find more polyunsaturated fat in their meat. This does depend a little bit on the species, and I'll go into that in a few slides. But the point is that you will find a mixture of different fatty acids and types of fatty acids in whatever source you're getting the fat from, okay? So olive oil does not have only monounsaturated fatty acids. Animal fats do not only have saturated fatty acids. And in fact, they do not only have just one fatty acid. So animal fats are fairly high in stearic acid as their main saturated fatty acid, but they also have palmitic acid. They also have other fatty acids. Okay, this is just the predominant form. There is rarely just one fatty acid or even type of fatty acid in a food source, and pretty much never happens. Now, the physical properties of the lipid from that food source, though, will be dependent on which fatty acids are present in the greatest amount, as they will determine more what that fat is like. And we'll get into that more in some future slides. Okay, so now we're going to categorize the lipids by their physical state. So that was by their molecular structure. We're classifying them as saturated, monounsaturated, or polyunsaturated. Now we're going to classify them by their physical state. So if at room temperature, if we're at room temperature, what we call fats will be solid. So if the lipid is solid at room temperature, it is called a fat. If it is liquid at room temperature, it is called an oil. Okay. And a key term here for this whole definition is that melting point is the temperature at which lipids liquefy. Now, I've already kind of talked about this, is that double bonds are going to lower the melting point. They're going to be liquid at a lower temperature than a molecule that does not have a double bond. Also, having more carbons will increase the melting point. And you just have to think about that, that image that I told you of molecules tumbling over each other. How easy is it for the molecule to tumble over each other? Okay, so the ones with double bonds, that's kind of easy to picture, right? They have a little bit of a rounded shape. They're not going to stack neatly. They will tumble. For the length of the fatty acid, just think about, a smaller one will be able to tumble over the other ones more easily than a longer fatty acid that is in that is stacked together. Okay. So to just kind of demonstrate like the level of melting point differences here. So this right here is 16 carbons with 0 double bond. This is palmitic acid, and its melting point is 63 degrees Celsius, or 145 degrees Fahrenheit. This next one with 18 carbons is stearic acid, and its melting point is just 7 degrees higher at 70 degrees Celsius, or 158 degrees Fahrenheit. Okay, so taking out 2 carbons here reduces the melting point by 7 degrees Celsius. Now here is oleic acid, which is 18 carbons and 1 double bond, and its melting point is 61 degrees Fahrenheit. So let's compare that against the 18.0. This was 70 degrees, sorry, I said 61 degrees Fahrenheit. The 16 degrees Celsius, let's keep talking about Celsius, 61 Fahrenheit. Okay, so comparing it against the stearic acid, which was 70 degrees Celsius at its melting point, we add a double bond, and the melting point is now 54 degrees Celsius lower. Okay, we take out 2 carbons, it's just 7 degrees Celsius lower. We add a double bond, it's 54 degrees Celsius lower than it was as a saturated fatty acid. Okay, we add a second double bond. This is linoleic acid, and still 18 carbons. So I haven't really fully described this. This is just shorthand in lipids. So you have a C, which stands for carbon. The next number is how many carbons there are. So there's 18. And then you have the colon. And after that is how many double bonds there are. All right. So this is an 18 carbon fatty acid chain with 1 double bond. And this is really common abbreviation nomenclature for fatty acids. Okay, so the 18.2 linoleic acid, its melting point is -5 degrees Celsius. And so by adding another double bond, we decrease the melting point by another 21 degrees Celsius. So here I'm just kind of pointing out, so by decreasing carbons or adding double bonds, both of those lower the melting point. The double bonds have a much greater effect than the lack of carbons, having fewer carbons. Okay. And that kind of makes sense. Like you can picture this, like this tumbling image that I put in your head, this happening more easily with these kinks and these double bonds than these still straight structures. Okay, and so I've already pointed out, like the fats and oils that we use, they are a combination of fatty acids. Oils, so when something is called an oil, they're mostly extracted from plants. Plants produce multiple different fatty acids, not just one. These are living things. They're not refineries that are producing just one thing. So just like plants may produce multiple types of carbohydrates, they also produce multiple types of fatty acids. And so altogether, all of the lipid products that are extracted from a plant is that plant's oil. Okay. It's not just one fatty acid. Or all of the lipids that are taken from an animal, like lard, tallow, or chicken fat, is that animal's fat. Now, don't confuse the fact that we call lipids from plants oils, but then classify them as fat. So here's what I want to point out here. Coconut oil, palm kernel oil, palm oil. Okay, we call them oil because they're extracted from plants, but if we are categorizing them based on their physical state at room temperature, these oils are fats. Okay, coconut oil, palm kernel oil, and palm oil are all solid at room temperature. Okay, so don't confuse that. It's like a categorization versus naming. Now, so fats based on our categorization criteria are fats that are solid at room temperature based on this categorization criteria. They tend to contain more saturated fatty acids. Okay, this dark brown set here, and much fewer polyunsaturated fatty acids, this lightest color, than oils. This in general. oils are going to contain a greater total of monounsaturated fatty acids and polyunsaturated fatty acids um, than fats. Okay, monounsaturated fatty acids and polyunsaturated fatty acids, because of those double bonds, both tend to be liquid at room temperature. So the more mono and polyunsaturated fatty acids that you have, the more likely your fat is, or your lipid, I should say, is going to be oil, is going to be liquid at room temperature. Now, the more polyunsaturated fat that you have, the definitely more likely that your lipid will be oil and liquid at room temperature. So in manufacturing foods, we will use these melting point properties to get the desired fat melting points of those foods. The book talks about how margarine can have varying levels of oleic acid, which is the main monounsaturated fatty acid in olive oil. And the amount of oleic acid, or olive oil if they choose to just add straight up olive oil, or if they are using some other oil, they could do that. The amount of that, mono or polyunsaturated oil that is added will determine how soft or even liquid the margarine is. If you've ever seen like I can't believe it's not butter, that is like a squirt thing, that's what I mean by like a liquid margarine. Another relevant example for today is meat substitutes. So with the plant-based meat, the goal is for the texture to still resemble meat. And the problem, though, is that, as you can see here, most plant-based lipids are oils. And most animal lipids are fats. We have chicken fat, beef fat, pork fat. And so if you are only using these oils, your texture is going to be very different. As soon as that hits the grill, or even if it's even before it really gets warm, it's going to liquefy. Versus animal fats, they don't, right? And so what the manufacturers of these fake meats will do is they'll use a combination of different oils, including some oil fats, like palm oil or coconut oil, and to give and they'll purposely add these coconut or palm oils to give the product a firmer texture that doesn't just melt as soon as it hits the grill. And it has a mouthfeel that more resembles an animal meat product when you're eating it. Now, the other thing that they can do for that is to use hydrogenated oils. And so what hydrogenation is the process of adding hydrogen atoms to an unsaturated lipid to increase its saturation level. Now, why would we want, well, first, how they do it, they have a catalyst, and they have the liquid oil, and they just bubble hydrogen through it, and the fatty acids in that oil will uptake the hydrogen, and it will go from like this oleic acid, and when you add hydrogens, they break that double bond, it adds the hydrogens, and it becomes stearic acid. So more, like we've said multiple times, more saturated fats makes an oil or fat more solid. And saturated fats means that it's saturated with hydrogen. And so that is what they're doing here. They are saturating the fatty acids with hydrogen to create, to change this from unsaturated to saturated fat. And so So what food scientists realize, they can do this, they can add more hydrogens and thus change the double bonds in the unsaturated fatty acids to single bonds and straighten out the molecules. And then they'll be more solid. And so they have the same quote unquote oil, like we've still just added soybean oil, for example, but with a more saturated profile and a firmer consistency. And so essentially they are turning an oil into a fat. Um, and this is how margarine can be made with 100% vegetable oils. Like, you've seen, some of the margarine says ingredients are hydrogenated corn oil, and it's like 100% corn oil. It's like, well, my corn oil that I bought just as corn oil in the grocery store is a liquid. How did it become this? It's because of hydrogenation. Um, so, why do they do this and not just use something that is already fat? So the advantages of this is they can achieve a longer shelf life compared especially to the original oils, but also even compared against lard, which is an animal fat that was used quite often before all of this technology came into existence. Um, it has greater stability. Oils tend to break down, and we'll talk more about that next week. But it's greater stability against oils or lard. And think about, so like lard, when I'm talking about lard, there's a portion of unsaturated fat in lard, and here they can make it, they're not going to completely saturate it because it would be, they saturate it to the level that they want. So you don't want it to be too hard. If it's all saturated fat, it would be a very very hard, very dense in the sense of compact, not dense as density versus water, but very compact structure, which would be hard to break through. So they don't completely saturate it, but they do enough that it has greater stability than lard, which is another like natural fat. This is lower cost than using lard or adding palm oil or coconut oil to the mixture. And finally, this one I added, I think there's a perception of better nutrition. Kind of back in the 90s when there was this anti-fat craze, which kind of leads us to where we are today, where a lot of fat is still considered really bad. Animal fats, saturated fats in particular, were considered the worst kinds of fats. And so lard and tallows were kind of demonized, and we went more towards the vegetable fats are better for you, but they're really not better for you if you completely changed their structure and made them more saturated and more like the animal fats. But there is this perception that the nutrition is better when you are eating an oil, margarine that, oil that is, this is 100% corn oil versus this is pig fat. So not really an advantage, but an advantage from a marketing standpoint. Okay, so the next type of fat that I want to go over, kind of, I had this originally in, and really the hydrogenated fat part could go in there too, in the molecular structure part of this section, but then I changed it because of the reasoning that we create hydrogenated and trans fats. So trans fats. So in most unsaturated fatty acids, okay, like this oleic acid here, the hydrogens and the double bonded carbons are on the same side. And that is why we get this kink in the molecule. Okay. The hydrogens are kind of like pushing everything down. Okay. And so trans fats, So what I was saying about a nice straight molecule lends itself to stacking nicely, forming a more compact, solid fat. A trans fat, even though it has a double bond, will do the same thing. This is a trans fat right here. Okay. And so what happens with the trans fat is that these hydrogens are on opposite sides. Okay. And so they've just modified the structure. It's still an 18-1 molecule. If I have that, abbreviation there, I would still say C18-1. Although I'd have to put a little T subnote there. But the hydrogens are just now on opposite sides. And so because they're on opposite sides, there's not this full pushing down, because one is pushing one way, the other one's pushing the other way, and it ends up straight. Okay. And so this trans fat, even though it has a double bond, from a physical property standpoint, it behaves more like a saturated fatty acid. Now, trans fats are found in nature only in very small amounts. They are found in meat and dairy products, but their levels are pretty negligible. There's not very much of them. But people figured out that they could create trans fats using a process similar to the hydrogenation process here. It's called partial hydrogenation. And in this partial hydrogenation, basically all they're doing is just moving the hydrogens around. And so in this way, they can use unsaturated fat and give it the physical properties of a saturated fat and still call it unsaturated fat. So this is how margarine used to be made, using vegetable oils that were partially hydrogenated to make them harder. Now, I forget when, probably, does it say in the book that they've been banned yet? I don't know. I don't think they had. Okay, yeah. So January 2006, the government, there had been a lot of research showing that these trans fats are not good for you. In fact, they are worse than saturated fat because your body does not know how to process artificial trans fats. The natural ones your body can process better, but these artificial ones that are man-made, not so much. And so these trans fats were actually leading to increased risk of heart disease, even worse than saturated fat. And so they weren't completely banned, but they're pretty much demonized to the point where it's like, hey, yeah, you need to get these out of this food, and you need to have it labeled if it is in there. Now there's and the book does describe this, how there's kind of like a loophole in the regulations where if in a serving size you have less than 0.49 grams per serving, you don't have to label trans fat on the nutritional label. And so it might say 0 grams trans fat, but there actually is trans fat. And if you are eating some things in several servings, you're like heaping your margarine onto your food, you might be getting a amount of trans fat that is not good for you. So things to watch out for is in the ingredient statement, if it says partially hydrogenated, whatever oil, it has trans fat in it. If it just says hydrogenated, then that's this process. They've just made it into saturated fat. But if it says partially hydrogenated oil, then they have trans fat as an ingredient in what you're eating, and it probably should be something that you avoid. Okay. So the third way that we can categorize the lipids is based on where we are sourcing them from, the dietary source. Um, and so we have a list of dietary sources and what those terms are referring to their source. So the first source is milk fats, and that one's pretty obvious, right? It's fat from milk of animals that we typically get milk from. So cows, goats, other mammals. Most of these fatty acids are shorter 4 to 12 carbon fatty acids. For example, one of those is butyric acid, and I guess kind of like trivia, but the word butyric comes from the Latin butyrum, which means butter. So there's butyric acid and butter. And this particular fatty acid, butyric acid, when it's by itself, it smells really lovely, like rancid butter or like smelly socks. And so that's so great. But sorry, I'm think of how I want to phrase this. So milk, the fatty acids in milk can tend to break down, and they will break down into these smaller short chain fatty acids. And so if you get that breakdown happening too much, then you end up with more butyric acid, and that's how you have like rancid milk, right? So when your milk smells rancid or like sweaty socks, it's really, really bad. It's because these fatty acids have actually broken down into 4 to 12 carbon chains. Okay. Milk fats are also high in palmitic, which is 16 carbon, oleic, 18 carbon, 1 double bond, and stearic, which is 18 carbon, 0 double bonds. Okay, the next dietary source is lauric acids. And so these are the main component of lipids found in the oils of fruit or seeds from tropical palm trees. So here we're talking coconut or palm kernel oils. Okay, they tend to be very saturated. They are the most saturated of the plant. Remember that naming versus classification, right? So they're called coconut oil or palm oil, but they are pretty saturated and solid at room temperature. And so they're named for lauric acid, which lauric acid is a 12 carbon saturated fatty acid, and that composes 40 to 50% of the total fatty acid profile of the lipids from these sources. The next dietary source we call vegetable butters, and so these are from seeds of tropical plants, and they're going to have at least, like for every triglyceride, they're going to have at least one unsaturated and one saturated fatty acid on every triglyceride molecule. Example here would be cocoa butter. Okay, so they are not as saturated as the lauric acids, but they are more saturated than other oils, and they, kind of have like a butter consistency. All right, so they are somewhat solid at room temperature because they are saturated enough to be solid at room temperature. The fourth one is the oleic linoleic acids. And so sources of these are corn, peanuts, sunflowers, olives, cottonseed, sesame seeds. So all of these create oils, right? They're going to have less than 20% saturation of their fatty acids. And the most common fatty acids, or most abundant, I should say, fatty acids in the oleic linoleic acids are oleic and linoleic acid. So oleic is an 18 carbon, 1 double bond fatty acid. Oleic is 18 carbon, 2 double bonds. Okay. So oleic, um, so in Latin, oleum means olive oil. And so that's what that comes from. Olive oil is predominantly oleic acid. It does have other fatty acids, just like all of them have a mixture, but oleic is predominant, olive oil is predominantly oleic acid. Okay. So now the fifth type is linolenic acid. So we add an N here, and that distinguishes linoleic, which has 2 double bonds, from linolenic, which has 3. So you add an N in the word, and it adds an extra one more double bond. So linolenic acid is abundant in canola, which is basically a crop that's grown just for canola oil. It's also known as rapeseed, which is not the most attractive name, so it kind of got rebranded and it's called canola. And also high in soybeans, wheat germ, chia, flaxseed, nuts. Now, we'll talk more about this in part 2 of this chapter, but the more double bonds that we have on a fatty acid, the less stable it is, and the more easy it is to become rancid. And so these oils are less stable and will go rancid more easily than anything we've talked about up to this point. So that's just something to know about those. Okay, so now the sixth one is animal fats. And that one's pretty obvious, right? They're going to be found in animals. So animal fats tend to be more saturated in general, therefore have a higher melting point, and are fats at room temperature. And the book does talk about marbling, which is a name for the streaks of visible fat that's scattered through the muscle fibers. And marbling is really good indication of flavor, of tenderness, of in my opinion, goodness. Now, that does mean it has more fat. So if you are looking for a lean cut that has less fat in it, you don't want to find something that has marbling. But here's an example of marbling in a steak, right? So all these flecks of fat are marbling. This is just fat that is distributed through the muscle fibers. This right here, this big chunk of fat, that's not marbling. That's just fat that is between muscles, not muscle fibers. This isn't marbling, but the flex is what is marbling. Okay. The more marbling, like I said, more flavorful, more tender the meat will be. Fat is flavor, and we'll talk about other things that it does next week. So the high melting point of animal fats is actually kind of important. In biology, there's a reason that animal fats are more saturated. So with saturated fats, when they are nicely stacking together, that is a more efficient way to store the fat, if they can be stored more compactly in the tissues. Okay, and we want to store our energy stores efficiently. So in general, animals produce the most saturated fat, that is like the highest saturation level that they can achieve, while still being relatively liquid at their normal body temperature in their normal environment. Okay, so mammals, they're warm-blooded, and so they have a higher body temperature, and so that melting point if they're trying for it to be as saturated as it can, that melting point is going to need to be higher than that of plants, of most plants. Okay, so kind of a cool fact, and it will vary based on environment, how warm that animal is, etc. So, cool fact, in animals in the winter, as you go down their extremities, like down towards their hoofs, the fat will become more unsaturated because the temperatures in those extremities are cooler in the winter compared to the main body of the animal. So down at the bottom of their legs, the fat cannot be as saturated because it would solidify in their bodies, and they don't want that, right? So it still needs to be liquid. So it has to be more unsaturated down in their extremities than in the main part of their body. Conversely, abdominal fat in animals, which is the part that's always going to be, at animal body temperature, and isn't affected by the elements really, that tends to be more saturated than any part that has more exposure to the elements, that's closer to the outside of the body and can therefore get cooler. Now this actually applies to the fats that we mentioned previously. It also applies to plant fats. So plant fats also will be as saturated as they can be and still be liquid at the temperature that those plants are living at. And so that is why our tropical plants, like our coconuts and our cocoa, and have oils that are more saturated because they are in warmer environments. And so those oils will be more saturated because they'll be liquid still in those hot tropical environments compared to plants that are grown in the middle of North America, like cottonseed or corn or what have you. So there are, I kind of mentioned this earlier, there are also some differences in the animal type and ability to produce unsaturated fats. The biology of ruminants, which include cattle and sheep, animals with more than one chamber to their stomach, their biology makes them generally predisposed to produce more saturated fat. It's just the products of digestion produce a lot of saturated fat in general. Whereas monogastrics, animals with just a one-chambered stomach, tend to convert the fat profile of what they eat more directly to what is deposited on their body. So like pigs are more what they eat. Chickens are more what they eat. But cattle, it's harder to affect the fat profile of the meat by feeding them a different diet. Okay, so finally, last one, I know I'm going a little bit long on this lecture, is marine oils. And so those are the fats in fish. And the key distinguishing factor there is that the fats in fish have a large amount of long chain unsaturated polyunsaturated fatty acids, I should say. So they'll have a lot of the unsaturated fatty acids has 5 or 6 double bonds, which is a lot, way more than any other fat source. And because of that, because it is so polyunsaturated, those oils tend to go rancid very quickly. And that's one of the reasons that fish don't keep well in the refrigerator. They need to be frozen or eaten quickly. Now, I did want to show here, so what I was talking about with beef being more saturated, you can see that here. So this is like percent of all the fatty acids, how much is saturated, monounsaturated, polyunsaturated. So chicken tends to be more polyunsaturated than pork or beef, and as well as more just unsaturated in general than pork or beef. And beef tends to be more saturated than either of the other two. And then fish is in its whole different world. So this is just a generic fish oil stat that I found online. It's going to vary a little bit by the type of fish, but just kind of in general here, the polyunsaturated fatty acids in fish are through the roof compared to our land animals here, at nearly 70% of the total overall fatty acid profile. And the saturated and monounsaturated are far less. So just wanted to show you that. Okay, so that is it for this week. And the next week we'll start going through more functionality and nutrition of fats.